So in the last video I introduced the basic idea of homology groups, and in this video I want to carry on with that and explain a few more ideas in the same circle of things. So one point I want to start with is, so let's just recall the kind of situation. We have maybe a space X like this, and we wanted to consider, for example, a path here. We'll call this path U with endpoints A and B. So one thing we didn't really emphasise in the last video that I want to say something about now is that in the full theory that we're going to develop later, everything will actually have a direction to it. So before we said that the boundary of U consisted of A and B, and that's still going to consist of A and B, but we're going to have some signs attached to this. We're going to say the boundary of U is B minus A. Okay. So you might ask, what does this minus mean, right? We're not. How do we subtract points in X? Well, the answer is, it doesn't really mean anything in particular. We're just taking kind of formal expressions, formal linear combinations of points of X with integer coefficients. So we don't actually have to attach any sort of special meaning to this subtraction operation. It's just B minus A is just whatever it is. Okay. So this is a kind of a substitute, a slightly more refined version of just the set AB, which is what we previously said the boundary was. And so we're going to have this sort of addition and subtraction type thing, and addition is kind of more or less just like taking the union. The full story is a little bit more complicated than that, but that's roughly how it goes. So that's how it works kind of for a path. And then similarly, when we do sort of two-dimensional things like this, here we might have a region that we're going to call P, and deep, and so then we've got the boundary of this is going to be this path going around here that we're going to call V, and the rule is going to be that dP is going to be V running anti-clockwise. Okay. Again, it's going to be a more complicated story later on, but for the moment, let's just take that to be the rule. So, but then this V running anti-clockwise so this is going to count the same as minus V running clockwise. Okay, if U denotes this path here, then minus U denotes the same path running in the opposite direction. V denotes this loop around the green region. Minus V denotes the same thing, but going the other way around. And so dP is V going this anti-clockwise direction, or minus the thing going the other way around. Okay, so there's going to be these rules like this, which we'll need to explain in more detail later. Then the next thing I wanted to mention was about returning to this idea that how we detect holes. So we mentioned that we could detect this hole by considering this path here. Let's call this one U, and so U is it's a path that has no boundary. So that's a cycle, but we can't fill it in whilst working wholly within the space X. So it's a cycle that's not a boundary, so it reveals the existence of that hole. Now let's consider this path here. Let's call this one V. Okay. So now the point is that U and V they detect the same hole. Okay, so there's no real interesting difference. If we're just interested in counting the holes, there's no interesting difference between U and V. So how do we formulate that mathematically? Well, the point is that although U and V are individually not boundaries, the kind of space between them is a boundary. Well, the difference between them is a boundary, right? We can't fill in U itself, but and we can't fill in V, but we can fill in the space between U and V. So we call this thing P. So what's dP? Well, dP is so part of it is going to be V, right? So you go, as we said around here, the rule is that you go anti-clockwise, so the region is on your left. Okay, so we go around the boundary here, keeping the region on our left. That gives V. But then the other thing that we have to do in the other part of the boundary is this U. And if we keep the region on our left, then we have to go in the opposite direction. We have to go clockwise. Okay, so that's that counts as so the boundary. If we keep walking around with the region on our left, the boundary is V in the usual anti-clockwise direction, and U reversed, which counts as V minus U. So U, V not individually boundaries. But V minus U is a boundary. And so in that sense, U and V are equivalent. So this hopefully might ring a few bells, something that you've kind of seen before. This is it should remind you of how we form quotient groups. So this is what we're going to do. And find Z1 is the set of one-dimensional things with no boundary. Okay, I should clarify what I mean by one-dimensional here, right? I mean these paths, right? If you look at a small piece of a path, then that looks like a small piece of R over 1, okay? And so for that reason, we think of paths as being intrinsically one-dimensional. Even if they kind of curl around in 2 dimensions or 3 dimensions or whatever, we think of them as being intrinsically one-dimensional because any small piece of a path is like R over 1. So here when we say one-dimensional things, we basically mean paths. Paths with no boundary. And B1x, or in other words, this is a set of 1 cycles of dimension 1. And then B1x is a set of one-dimensional boundaries. Right? And as we said, every boundary is a cycle, so this is actually a subgroup of Z1x. And H1x is going to be the quotient group. That's a set of cosets like U plus B1x. Where U is a cycle. Okay. So going back to this example here, we had that here U minus V it's the boundary of something, so it lies in B1x. So the coset U plus B1x is the same as the coset V plus B1x. These as elements of the homology group H1x. Okay. The idea is that H1x is kind of a group whose elements are basically are the holes, or in some sense, and so U and V, they give us the same element of H1, so that means that they indicate the existence of the same holes. So that will do for this video.